your lunch, and we should get started. I can still see people coming in. Okay, have a seat. So the first oral session will be chaired by Professor Mohammed Yaqub from Mohammed bin Zayed University of Artificial Intelligence. So I will pass over to Mohammed to introduce our first speaker. And if you can find your seat as soon as possible and be quiet, please. Thank you.
Thank you, Gautam. Welcome back, everyone. So this will be an interesting session about image classification. We have three speakers. The first speaker is from Japan, who will be providing the presentation online. So the paper entitled Deep Bayesian Active Learning to Rank for Endoscopic Image Data. Welcome. Please start.
Thank you. Thank you for your introduction. Hello, everyone. My name is Takeaki Karata from Kyushu University. Today, I'd like to introduce our work, Deep Bayesian Active Learning to Rank for Endoscopic Image Data. First, we briefly introduce the estimation of disease severity. For image-based estimation of disease severity, it is common to prepare training samples with severity levels annotated by medical experts. Standard annotation, hereafter called absolute annotation, assumed discretized severity levels. However, absolute annotation is often difficult to reach an agreement among medical experts. This is because disease severity is not discrete in nature, and thus there are many ambiguous cases. For example, when annotating medical images with 4 discrete levels, 0, 1, 2, and 3, they will frequently encounter medical images with severity of 1.5. A promising alternative annotation approach is relative annotation. Relative annotation compared two images for their severity and attached relative labels that indicate the comparison result. Relative labels are not discretized severity labels and are easier to annotate. A practical problem of relative annotation is that we must select appropriate image pairs to annotate from all possible pairs. This is because the number of pairs increase quadratically with the number of image samples. Since the number of pairs would be very large if relative annotation were performed on all pairs, it is necessary to select the pair with the best learning effect. Therefore, we propose a deep Bayesian active learning to rank to select the effective learning pairs. Our method combines a learning to rank framework with Bayesian CNN to estimate model uncertainty. Using images with high uncertainty, we create a small number of practical learning pairs. This is an overview of the proposed method. The deep Bayesian active learning to rank consists of 3 steps. In step 1, we create an initial training dataset. In step 2, a Bayesian CNN is trained with labeled image pairs. In step 3, pairs are created based on the estimated uncertainty and added to training dataset. Step 2 and step 3 are repeated to train Bayesian CNN, while gradually increasing the number of training data. First, we randomly sampled R% from the unlabeled image set and create pairs. To reduce the number of pairs for annotation, each R samples is randomly paired with one of the R-1 samples. Relative labels are attached to these image pairs by medical experts. Then, the learning to rank framework RankNet is trained with the labeled image pair set. RankNet is trained as a Bayesian CNN using Monte Carlo dropout. The loss function for learning to rank is cross entropy. This function learns to bring the sigmoid function of difference of the output values closer to relative labels. In the next step, the model uncertainty is estimated using MC dropout. When estimating rank score, we use dropout for Bayesian CNN. Dropout causes rank score to change with each iteration. The uncertainty is defined as the rank score estimated multiple times. The S% images with high uncertainty are sampled and paired are created. In addition, relative annotation are performed by medical experts. The annotated pairs are added to training data and the Bayesian CNN is trained again. Step 2 and step 3 are repeated to increase training data gradually. We use a data set with absolute stability levels, Mayo scores, for ulcerative colitis UC. This data set was used to analyze the relationship between absolute stability levels and estimated rank score. A Mayo score was annotated for each image on a 4-level scale. This data set has imbalanced classifiers. We compared our method with 2 baselines and 1 ablation study. Baseline is a method that randomly samples the same number of pairs as the proposed method without repetitions of active learning. Baseline's all data is a method that uses all n training pairs without repetitions of active learning. Proposed without uncertainty-based sampling, UBS selects additional training data by random sampling. As the accuracy evaluation, we measure the correctness of the estimated rank scores in a relative manner. Comparison of disease severity can be considered as the estimation of treatment effect. For the test data set, we prepared 2 types of pairs. Overall test data set randomly paired among all Mayo. Using this test data set, we estimated the overall performance of comparative methods. Neighboring test data set are created paired at the neighboring levels, such as Mayo 01, Mayo 12, or Mayo 23 pairs. This estimation is more difficult because the disease severity gradually changes in the neighboring Mayo, and these image features are similar. This is an experimental result of quantitative performance evaluation. In the overall test data set, the proposed method was better than all comparative methods. Surprisingly, the proposed method was better than baseline all data, although our method training data is half that of baseline all data. In the neighboring test dataset, the proposal method was also better than all comparative methods. The proposal method improves the accuracy in the cases Mayo 2-3 by over 10%. This figure accuracy of estimated relative labels at each labeling ratio. Horizontal axis indicates labeling ratio, vertical axis indicates accuracy. The proposed method includes the accuracy with the number of training data. In contrast, for baselines and proposed without UBS, it was not always true to include the accuracy by increasing the training data. We consider that our method improved because our uncertainty-based sampling reduced class imbalance. Therefore, we investigated the relationship between the uncertainty and the number of Mayo labels of sampled images. This figure shows a class population of sampled images at each labeling ratio. Vertical axis indicates number of images. Our uncertainty-based sampling selected many samples of minor Mayo level, Mayo 2, and Mayo 3. The class imbalance was gradually reduced as the labeling ratio increased. This figure shows distribution of the model uncertainty in each class. In baseline, the uncertainty of minor classes Mayo 2 and Mayo 3 was higher than the major classes Mayo 1, Mayo 0, and Mayo 1. In the proposed method, the uncertainty of Mayo 2 and Mayo 3 was lower than those of baseline. This result indicates that the fewer class samples are, the higher the uncertainty. Finally, we show an example of application of the proposed method. In clinical, medical expert checks all images, find the most severe images, and diagnose the severity of UC. This figure shows 3 examples of the changes in the rank score. The horizontal axis indicates the capturing order in a sequence. Vertical axis indicates the estimate rank score. Using this graph, medical doctors can easily check if the disease is severity or not, and find the severity area and check them. It is also easy to show both cases before and after treatment and diagnose the recovery of the disease. This is a summary and future work. In summary, we propose a deep Bayesian active learning to rank for efficient relative annotation. The experiment result indicated the usefulness uncertainty-based active learning for selecting samples for better ranking. we also reveal that the proposed method shows the robustness to class imbalance. In future work, we plan to improve the proposed method to estimate the severity levels of UC using a small number of absolute levels to make it easier to use in clinical practice. Thank you very much for your attention.
Thank you very much for the interesting work. Any question from the audience? Maybe I could start with one question where you ended up your talk. Currently, as it is, the paper or the work you've done does not translate to clinical practice where you provide with a score. How do you see your work taking that relative comparison to physical Mayo Clinic score, for instance?
Mayo Clinic. Yes. We considered when we use this proposed method, we use doctor know both cases before and after treatment. So rank score, when we use rank score, we can know Mayo score. So in the future work, in future work, we will combine learning to rank and regression to calibrate rank score to Mayo score.
Okay, thank you. I see on the online chat that Gorkem, if I read the name correctly, you have a question. I'm not sure if you can speak.
Yeah, hi. Can you hear me?
Yes.
Oh,
please
okay.
go ahead.
Yeah, okay. Thank you for the nice presentation. What I would like to ask is that I see that your performance metric is accuracy, right? Is it your main performance metric?
Mayo performance.
Is that accuracy?
Sorry, I can't understand.
Can you come to the slide 11?
Slide 11. Okay.
Okay. I see that your main performance metric is the accuracy, right? I mean, these numbers represent the accuracies.
Accuracies. This accuracies is disease order. This accuracy is disease order of pairs. For example, we evaluated the correct of disease order. For example, Mayo 2 or Mayo 3. So when we evaluated accuracy, we use 2 images.
Okay, there is an overall column in the slide 11. What does that overall mean? I mean, accuracy for the 4 classes?
4 classes. Overall test data set. We create overall data sets are created paired. For example, 01, 02, 03, 12, 13. So neighboring test data set only 01 or 12 or 23 test data set.
Okay, what I suspect is that your performance might be higher because there is a serious class imbalance in the data set, right? The majority of the images are from Mayo 0. And I see that the the differentiation between 1 and 2 and 2 and 3 is much higher than the baseline. Therefore, what I suspect is that your performance increase might be much higher in another performance metric.
Okay. Yes. Our data set has imbalance data set. Baseline has large imbalance, but our proposed method training data set class imbalance was reduced. So
can I just interrupt here, Mr. Kadota? I think both of you are online. If I may just propose that you can take that offline for discussion. It's an interesting one, but for the sake of time, we would like to thank you again and move on to the next one. Thank you very much.
Okay, thank you.
Thank you. So next speaker, please present here. The paper is entitled Improving Image Representation via MoCo Pre-Training for Multimodal CXR Classification.
Hello, everyone. I'm Francesco, and I'm an NHD student with Canon Medical Research Europe and the University of Glasgow. And today I will be presenting the work entitled Improving Image Representations via MoCo Pre-Training for Multimodal Chest X-ray Classification. So in this work, we focus on multimodal learning, so including not just the chest X-ray image, but additional textual information. We consider the task of chest X-ray classification of 14 different classes, and we focus on image component of the multimodal transformer architecture, which originally was introduced for NLP, and now it's also the state of the art for multimodal classification in the general domain. We consider some self-supervised learning approaches because we want to start from a better image representation than the usual ImageNet pre-training weights that are commonly used in the general domain. And finally, we also perform the same experiments considering a limited training set by reducing it to 10%. That's due to the fact that usually multimodal data set are quite small, generally quite small. So here there's an overview of the proposed architecture. So the two modalities we're considering are the chest X-ray. We only focus on frontal views, so anterior, posterior, and posterior, anterior. And the indication field, which is the part of the radiology report, which gives some relevant medical history of the patient or the reason why the scan was taken. And yeah, there is an example on the top where like the patient arrived with shortness of breath, and that gives additional context to the model to classify. And the 14 classes we are interested in are listed below, and are atelectasis, cardiomegaly, consolidation, edema, enlarged cardiomediastinum, fracture, lung lesion, opacity, pleural effusion, pleural other, pneumonia, pneumothorax, and support devices. And there is an additional class not finding when the scan is normal. And so, as I already mentioned, in this work, we focus on the image encoder component, and we focus on self-supervised pre-training strategies, since there's no need of having expert annotation. And here are some of the pre-training strategies we took in consideration. So the top is the supervised ImageNet pre-training weights, which are commonly used for CNNs architectures, and they're easy to find already available for most of the classic networks. But the problem is that they're trained on natural images and not on medical images. While the three methods below, the autoencoder, Sinclair and Moko. So the first one, the autoencoder, is quite easy to train and does not require large batches to train, and it's trained on reconstruction loss. The Sinclair momentum contrast pre-training are contrastive learning approaches. And the first one has the problem that it requires very large batches that are larger than thousands of images, while the second one is designed to work also with smaller batches. And this method can be used for pre-training on medical images. And they all not require labels. So as I said, we didn't actually consider Sinclair at the end because we train on a single GPU. So the batch required was too large. Here are the two consider self-supervised approaches. On top, the autoencoder, which is ResNet 50, both for the encoder and the decoder. The second one is momentum contrast, which has a query encoder, a key encoder, which are both a ResNet 50, and the multi-layer perceptron head is two fully connected layer, and then they're trained using a contrastive loss. And for Moko training, like it works as other contrastive learning approaches, where the aim is to minimize the embedding distance between two positive pairs, which are two augmented versions of the same image, and it tries to maximize the distance with all other images in the data set. Here is an overview of the proposed pipeline. So on the top left of the figure, there is the Moko pre-training. Then we use the query encoder to initialize the weights of the image encoder in the multimodal model. And finally, we fine-tune the multimodal B transformer, or MMBT, on the 14 classes. And this is as BERT as a backbone, which is a transformer encoder model. And the images embedding are flattened to obtain, so the 7x7 embedding outputted by ResNet 50 are flattened to obtain 49 image tokens defined as I. Then the text tokens of the indication field are tokenized into M word embeddings, W. And we also use a classification token at the beginning of the input sequence, and the final hidden representation is used as the multimodal sequence representation for classification. And as separation token, SEP is used to separate the two modalities, the image and textual modalities. And both input modalities are then summed by a positional encoding and a segment encoding. And we consider two data sets, chest X-ray data set. The first one is CheckSpert, which contains roughly 200,000 chest X-ray images of 65,000 patients. And we treated it as an unlabeled data set, although it has labels. And the multimodal data set we consider is Mimic CXR, which is the largest chest X-ray, multimodal chest X-ray data set, open source data set, which also contains roughly the same number of image and report pairs, and also around the same number of patients. And it also has 14 labels that I already described, listed before, associated with each image, and these are automatically extracted from the report. And as I said, we also consider the same experiments by reducing the training set to 10% of the original. We compare also the MMBT with 3 baseline, text-only baseline, which is BERT model, which only takes the indication field as input without considering the chest X-ray. And as the image only, we consider the ResNet 50 only. In this case, the model only uses the chest X-ray to classify the 14 images. And we also compared with another multimodal approach, which we define as attentive. This doesn't use a transformer architecture, but rather it uses 2 sequential bidirectional gated recurrent units, and then the visual and textual features are merged using 2 multimodal attention layers. We can now see the results on the Mimic CXR test set, comparing the different image pre-training strategies. On the top, we have the results using the full training set, and on the bottom table, only using 10% of the training set. So the first thing we can notice is that both multimodal approaches improve the unimodal baselines, with MMBT being the best solution. Here we compare using the standard supervised ImageNet pre-training. But when reducing to 10%, the gap between multimodal and unimodal approaches is now reduced. And actually, for some of the metrics, the ResNet 50 only beats the other multimodal approach, the attentive. When looking closely at the MMBT results, we see that not all the domain-specific pre-training, so the autoencoder and the momentum contrast, are yield better performances than ImageNet. So the autoencoder actually doesn't seem to be as efficient as using contrastive learning. And however, in the 10% scenario, we have that both domain-specific pre-training have achieves better performances than ImageNet. And for all 3 image-based approaches, so ResNet 50, attentive, and MMBT, we find that using Moko pre-train on CheckSpert achieves better performances than ImageNet. And the gap is also increased when improved when we consider the limited data scenario. We finally wanted to assess the quality of the attention activation map using supervised ImageNet pre-training and Moko pre-training on CheckSpert. And to do so, we consider another data set, which is chest X-ray 8, which it contains bounding boxes annotation for 8 classes, and we only consider the classes that overlap on Mimic CXR. So atelectasis is the one that are highlighted in bold. And to do so, we fine-tuned only the fully connected layer after the pre-training stage, and we apply GradCam on the final 7x7 activation map. We compute and then we compute the intersection over union between the regions that have positive activation for a specific class and with the annotated bounding box. So on the left are the IOU results, and we can see that using Moko, the IOU are better, although they're still the number are quite low. That can be due to the fact that it's quite a small activation map. It's at 7x7, and also because we only fine-tune the final fully connected layer. And we can see that on the figure on the right, there's the positive activation maps are highlighted in green. And for Moko pre-training, the model seems to, with Moko pre-training, the model seems to localize better the pathologies in the image. But and while with using ImageNet, with the activation map seems more sparse. And we can have a closer look for two examples. And but yeah, on the right, it can be seen that also Moko, using contrasted learning, this doesn't achieve always good localization of the pathology. So in conclusion, our contribution are to compare different pre-training strategies for multimodal learning using an autoencoder, momentum contrast, and the standard supervised ImageNet pre-training. And we found that Moko to perform best. We explore how these strategies degrade when using a smaller subset of the training set. Again, finding Moko to be the best solution we explored, and we demonstrate that pre-training the image encoder on chest X-ray, it also achieves better performances for multimodal, multi-label classification. And finally, we evaluate using GradCam the impact of the pre-training, looking at the activation map, and we report some quantitative results on a small subset of the chest X-ray 8 test set. Thank you for the attention, and I'm happy to answer to any questions.
Thank you, Francesco. Any question? Here, please.
Thank you, Francisco, for your presentation. Just two related questions. Is the best performing multimodal model, does it have more parameters than the other ones you compare against? And can you give any reasons why in the experiment where you use 10% of the training data set, why the differences become smaller between the different models and the different training, pre-training approaches?
So yeah, thank you for the question. So to answer to the first questions, yes, the attentive model has less parameters compared to a larger transformer model. That was, we wanted to see the impact of using a transformer rather than other approaches using like recurrent neural network. And to answer to the second question, sorry, can you repeat this?
So you mentioned when you were talking about the second table that the difference in the improvement is smaller with a 10% training set. And I'm just wondering if you can give any reasons why.
You mean, okay, you mean between the two unimodal baselines compared to the multimodal baselines? Like in this example, like you can see that also ResNet 50 alone achieves here we're talking when using the standards supervised ImageNet pre-training. The ResNet 50 alone compares as good as the multimodal attentive model. And I don't have really an answer to this question, but I would say is due to the fact that it doesn't have enough training samples to fuse together the two modalities using the attentive model, although when using a larger model such as the MMBT, that's not the case anymore. It's able to learn more effectively the two, how to use the two modalities together.
Thank you. Any other questions? Room for one more question, sorry. Okay, I don't know who was first, so we'll go here, sorry. On this. Yes.
Yeah, thanks for the nice talk. I do have two short questions. The first one is about the pre-processing. Did you do any pre-processing on the X-rays? And if so, what kind? And how did you decide on the cropping as input for your network? And what was the sizes? And did you try different sizes? And then for the evaluation, did you check if your model was picking up on labels? Because that's something we experienced with COVID diagnosis, that it picks up like PAAP level labels on the X-rays.
So to answer to, can you repeat the first question?
So the first question was about the pre-processing.
Okay, yeah, the pre-processing. So we didn't do any specific type of pre-processing. We just used the chest X-ray image. We used quite a small, to be honest, a small image size. So it's 224 by 224. That's mainly due to the fact that the model is already quite large and it would take too long to train using a bigger resolution, larger resolution. And the second question, sorry again.
It was about the heat maps at the end.
Okay.
If you also experienced that it looks at the image labels, like for example, in the first row on from the second from the right, I think on the left top, that might be some label. I don't know. I can't see it.
Oh, yeah.
If you experience that it might pick up some labels that are on the X-rays.
So you mean like, oh, you mean the
Some writing.
Some writing. Okay, I see. Yeah, we found that actually, if you look at ImageNet, but there are some cases that it activates on the top left corner, which is usually when it describes if it's anterior, posterior, or PA scan, and yeah, it still has some cases where that's often happening. Yeah.
Okay, so that's also happening with MoCo, with ImageNet and MoCo.
Mm-hmm. Yeah.
Thank you.
Thank you very much. Apologies to people who would like to ask questions. I highly encourage you to take these questions offline. Yeah. Thank you, Francesco, again.
Thank
Thanks.
you.
And next, I would like to invite the speaker for the paper entitled Multiscale Graph Neural Networks for Mammography Classification and Abnormality Detection.
So hi everyone, and thank you for the opportunity to talk about my work. So my name is Guillaume Pelouet, and I am a PhD student in the University of Nantes in France, and with the company named Erami. And our work is entitled Multiscale Graph Neural Networks for Mammography Classification and Abnormality Detection. So for context, early breast cancer diagnosis and lesion detection have been made possible through medical imaging modalities such as mammography, which is the most common method in breast imaging. However, the mammography is the interpretation of mammograms by a radiologist is still challenging. So this figure is an example of a complete mammography exam with two views. From the left on the breast and the left on the right breast. So current deep learning methods built on convolutional neural networks have demonstrated good performance in the task of automated analysis of individual mammograms. For example, for the task of malignance or region classification, as shown in this figure, they mostly use a supervised approach, which requires a region-wise delineation, which is not part of the clinical protocols. So this is an example on one of the state-of-the-art method in mammography classification, where they are doing region-wise classification and region-wise delineation in input, which requires an input of the model region-wise delineation, which is not, as said previously, not part of the clinical protocol, and it's very time-consuming for experts. Due to this fact, we are constrained to a weekly supervised approach in our mammogram classification pipeline. We use a weekly training method to train our model, called multiple instance learning, and introduced by Shukroon et al. In 2017. So it performs region-wise training through patches while evaluating only with image-wise label. So a Euclidean method like CNN and patches approach or convolution do not preserve topological information. As we can see in this example on the left, where we have patches, which could be also assimilated to pixels in the image. And all these patches have the same number of neighbors. So they have all the same topological information. In other hand, non-Euclidean approach using superpixel-based graph for example, provide informative topological information of the area of the abnormalities of the tumors and could adjust to the shape of abnormalities. We also use a multi-scale superpixels approach to handle the abnormalities variability in size or in the height range of size in the breast. So to learn this nodes on topological features, we choose to use graph convolutional network, which will, following the multiple instance learning strategy, perform image-wise and region-wise classification while having only mammogram labels. Now that we have defined our multi-scale graph, we can define the baseline method. So this baseline method was trained in our company with a private dataset, and it's named ResNet 22. It's a custom ResNet 22, which is following the multiple instance learning strategy to handle low annotation in the training process. So in the next slide, we'll refer to this network as a baseline B. So now that we have defined our graph and its associated node features, we can now train our graph convolutional network to classify the mammogram in 3 steps. So the first step is the multi-scale graph generation, which will generate a graph from a mammogram. The second step is the features extraction. So this is the step where we include a baseline network, a network where which we want to improve their results with while including topological information. And the third step is the graph convolutional network training part. So this is an example, an illustration of our graph generation process, where we can see that we fed to the process our mammogram, and with a superpixel algorithm will generate a multi-scale over segmentation. So this is an example there of a multi-scale segmentation of our mammograms. And with this over segmentation, we generate our graph, where each superpixel is a node in our graph, and each node is connected to in the spatial domain to their 4 connected neighbors and to the neighbors across scales to leverage topological information through the height variability of the size, the shape of the abnormalities. Now that we have our clusters, we use the baseline B method to extract features from superpixels through bounding box, as the baseline needs only Euclidean information, and superpixels are non-Euclidean information. This process allows us to have a graph with representative features for each node. So for each node, we also concatenated spatial features to the vectors of extracted features from the ResNet, which is the spatial coordinates of the barycenter of each superpixel with the index of the scale where we have the superpixel, where the superpixel was computed. In this third step, we want to extract 2 outputs. The first one is a global classification of our mammogram. So our GCN takes in input the graph composed of nodes and edges with features extracted from the baseline and compute a global classification of the graph through node classification. So we applied a max pooling to the node classification to obtain the final global classification, as explained in the multiple instance learning approach. So this is our first output. The second output is a region-wise classification of the mammogram, where we use the malignancy probability of each node to look for the model explainability and the localization purpose for radiologists. With our pipeline, we aim to perform 2 tasks. The first one is a global classification task, where we want to extract the probability of malignancy of the mammograms. And the second one is a region-wise classification, where we want to obtain a localization of the abnormalities which was detected in the breast, malignant probabilities in the breast. So to do so, we use 2 different datasets. The first one is the public dataset, which is called InBreast. So it's composed of 410 mammograms coming from 1 vendors. And we also have a region-wise ground truth for the evaluation purpose. And we use it for the testing part. The second dataset is used for the training and testing part and is our private dataset. It is composed of 3,162 mammograms coming from 4 different vendors to be more generalizable during the training process and do not overlapping the first public dataset in breast. So this is our 2 models that we want in the first time to compare. The first one, as explained, is our baseline. And so it is a model we want to improve the results with a topological, including topological information. And the second one is our final model with graph, which is MS GCN. So first we did an ablation of our model. So we compare the result in terms of global and region-wise classification for the baseline. We also fed to the baseline our superpixel extracted from multiscales. And finally, we compare with our final MS GCN, which is fed with graph. So we can see that superpixels on the GCN to include topological information improves the result in terms of both detection and classification task, while generating also more false positive per image comparing to the other Euclidean approach. In a second time, we compare our method to to the state-of-the-art method, showing that our weakly supervised approach do not reach the Ribli work, which is a state-of-the-art method in a mammogram classification, with an AUC of 0.95, which is the highest AUC we have for now. But we exceed the result in terms of detection task by 8% while using weakly annotated images for the training and including topological information. We also improve the detection task comparing to state-of-the-art method, while also having more false positive, per image. But compared to the other state-of-the-art method, which use a weakly supervised approach, we improve the detection, the TPR, while reducing by half the number of false positive per image. This shows the effectiveness of including topological information in the training process of Euclidean networks for image analysis. So this is an example of heat maps for the detection task. We can see in the first row a cluster of calcification, and the second column, is the baseline, where we see that it correctly finds the clusters, but with squares, so it's not precise. And our method, and it's on the fifth columns is the merge heat maps from each scales, found also the cluster of calcification. In the second row, we can see a small mass, which is also found by the baseline, but our method didn't find the mass, as we can see in the bottom of the red arrow. So we are not in the most intense area. But combining both the baseline and the heat map from our method, this allows us to improve the detection result in terms of segmentation in this illustration with the borders of the superpixels. So we are more precise in terms of segmentation for this illustration. So this figure is an illustration of our detection performance in terms of TPR and false positive per image. We can see that our method, the black curves in the figure, obtain the best result in terms of balance between TPR and false positive per image, which is always problematic. And when we look at the BG, so this is the red one, we merge the two methods. We can see that with an highest false positive per image rate, we have also an highest TPR. So we presented a new approach using the advantages of graph with a multi-scale approach to handle variability in abnormalities size and shape with the use of topological information. To continue this work, we could try this graph improvement on other state-of-the-art method like Ribli or Chen, which was a method I was comparing my performance. And we also can export this method to other medical imaging problematics, as abnormalities do not appear at a single scale nor at uniformly distributed in, for example, lung cancer, lung tumors, or liver tumors, for example. So thank you for listening, and do not hesitate.
I think we have room for a couple of questions. Question over there. Yeah. Can you just check the, can't hear you very well. I think we can lend her the other microphone if that's okay.
No. Thank you for your talk. I was wondering how you extract topological information. Do you use the entire pixels from the images, or you take landmarks and then you build your topology, use it as a topological vectors? Thanks.
Yes, so we cannot extract topological information with a Euclidean approach, as topological information do not exist in like a pixel relation when we do, for example, convolution kernels and things like that. So I use a clustering method where with superpixels, which allow me to cluster similar pixels into one biggest pixel, which is not a square pixels with, for example, an average intensity or features or texture features in this pixel. And this is, for example, this is an illustration of non-Euclidean information in the mammogram, where we do not see pixels, but superpixels. And this is how I can interpreted the topological information in the learning process of the GCN. This is the GCN which has a big part in the topological learning. As, for example, an example of topological information is, for example, if you look at some superpixel, we can see that superpixel do not have the same number of neighbors. So some superpixel in the, for example, in the fat in the breast. So it's the same intensity in the fat. Superpixel will be like a square, and they will have like 8 neighbors, where superpixel which will cluster pixels of tumors will have, for example, like a shape like that, like the white in the center. And we'll have not 8 neighbors, but for example, as the shape is not regular, so we'll have 6 neighbors, for example, and or 4 neighbors. And so this is how I fed the information to the graph convolutional network to interpret the topological information.
Room for one small short question, if there is. Derek is here.
Hi. First of all, thank you very much for your presentation. So my question is more regarding about the motivation of how you construct the graph. In graph learning, one of the most important thing is how you construct a strong graph. So you have this multi-scale representation and over segmentation. So my question is, what is the trade-off between over segment and over different scales? You can get a denser and denser graph that is going to increase the computational complexity, but at the same time, you perhaps in the different scales, you are over segmenting similar regions that might be repeating perhaps redundant features.
For example, a case where multi-scale help me to find the tumors is when I have a big tumors which correspond to the third scales, for example, so the biggest one. And so in the topological information, as I explained, are also not only on the neighbors between superpixel in the mammogram, but also between superpixel across scales. And so, for example, if you have a big superpixel which contour delineate the tumors, in the previous smaller scale, you will have the same superpixel, but divided in 4 or 10 superpixels with the same contours. And this is an interpretation of the multi-scale approach, but it's effectively it's constrained because it's multi-scale have a high computational cost. And I choose to use it because I also choose to use the easiest superpixels algorithm, which is constrained by at the input by the size of the final superpixels approximately.
Yeah, it was more about how much is the trade-off between the over segmentation, because when you over segment, you can choose about like if it's like how much you over segment. That's like let's say a K that is like a 2, 3 or something, and you're going to reach a point where it's closer to the pixel level. So
Oh,
you
yes.
construct a denser graph.
Yeah.
With the computational approaches.
So I didn't speak about the trade-off in this presentation. I use a formula which was explained in another papers, where it's based on the range of in the breast, in the anatomical range of in millimeters of abnormalities we can find in the breast. And I know that with my computational power, I will be limited to 4 scales. So with this formula, it gives me with my constraint on the trade-off, it gives me the trade-off for the superpixel for each scale. But it's a formula which I use.
Thank you both for the discussion. With that, I would like to conclude the image classification session with thanking all the speakers. Thank you very much.